Hi, my name is Emma and I'm a member of the team that created the Smart Sole. The amount of pressure application, as well as the exact positions of pressure application during activities such as running, jumping, landing, and heavy lifting have huge consequences on the possibility of injury during such activities. As shown before, 2 of our team members are currently in a boot dealing with an athletics-related lower leg injury. Those injuries could possibly have been prevented with a more informed knowledge of foot plyometrics and correcting these erroneous behaviors specific to a person's individual movement patterns. So, the motivation of this project is rooted in a lack of accessible, accurate, and specific resources to remotely guide athletes and non-athletes alike in their movement patterns. Healthy gait is methodical. Thus, this project aimed to create pressure-sensitive insoles for athletic form analysis to prevent those injuries. That was done by providing measurements and possible interventions to its user during physical activity. The pressure-sensitive insole includes an array of force-sensing resistors to measure mechanical stress dynamics within the shoe and achieve the shoe's main purpose. These insoles can be used either in a clinical setting or by a user on their own at home. Via a pressure-sensitive insole, the shoe can read, display, and analyze an athlete's gait and movement patterns during physical activity to prevent injury and improve biomechanical performance. It works via an array of force-sensing resistors, all connected in parallel. Each force-sensing resistor's pressure is measured with a voltage divider that feeds out to a microcontroller. We choose to use the ESP32 unit for this purpose, for its versatility and flexibility with wireless communication, since this was the most critical part of designing the Smart Sole for in vivo usability with an athlete.
The implementation of this project did not come without challenges. We ran into limitations with the ESP32 that prevented us from using as many force-sensing resistors as we would have liked to. So a further iteration of this project could allow us to improve. We were only able to use 6, but it would be ideal to use more. Using the Smart Sole is simple. You just insert the sole into your shoe and it wirelessly transmits the gait data via Wi-Fi to live user interfaces for data visualization and analysis. Next steps for the Smart Sole would be creating a second sole to compare pressure dynamics from foot to foot, as well as investigating how to improve processing speed to minimize the lag between sampling and displaying the data on the user-friendly interface. Another further direction would be completing the build-out with an accelerometer. This way, one could collect interesting metadata about your gait. For example, are you more prone to injury during a sprint, or do you pronate as you run? Lastly, we would like to explore how to operate the device via Bluetooth rather than via a Wi-Fi network, as this could allow the project to be used in more remote locations or from any device with Bluetooth capabilities without the need for Wi-Fi. We had a lot of fun creating the Smart Sole, and we are super excited to see what will come of our creation and what we learned from building it.